Welcome to the morning session of the second day of the second conference day of DeepSec. I'm looking forward to the talk Attacking SMS by Zane Lackey and Louis Miras. Yeah, you have
Thank
the
you.
word.
Thank you for getting up early this morning to come to our presentation. This is Attacking SMS. My name is Luis Miras. I'm an independent security researcher. And this is my co-presenter, Zane Lackey. He's a senior security consultant at ISEC Partners. And this talk is going to cover different ways that SMS messaging can affect mobile security. And to begin, we're going to start off right away with a short introductory demo. This demo is going to show how we're bypassing some carrier protections, specifically the anti-spoofing protections. What you're seeing here are two iPhones. These are real phones. These are not simulators. They're running VNC, so their displays are forwarded to us so that we could record it. On the left-hand side, you have the attacker. This is it's a proof of concept tool that we wrote to be able to spoof MMS messages, among other attacks. On the right-hand side, you have the victim. We have it on the contact screen to show that we are not doing any tricks to do the spoofing. There are no contacts in the phone right now. And what we're going to show here is that we're using the trusted number 611, at least in the US networks and other networks around the world. 611 is usually defaults to a carrier number. I'm not sure about here in Austria or Germany. And we're sending this message. This is actually traversing over a carrier in the US where we conducted our testing. So in a little bit, you'll see it on the right-hand side. So there you see a message coming from 611. It says that you've received a $20 credit and to please log into evil.com with your account credentials. So a user would see this and would assume that this is actually coming from their carrier and would most likely trust this and lose their credentials. There's probably a lot of questions about how this works, and we're going to be covering that during the rest of the talk. Some SMS background and how this affects mobile security. And then the next two sections, testing challenges in an attack environment, are very useful for people that might not be experienced in testing mobile devices or testing for SMS vulnerabilities. So maybe you're a pen tester, maybe you do web applications, maybe you reverse engineer, but whatever your background is, this provides you the information to get you started to be able to duplicate some of these things that we've done and for you to be able to do your own testing. Then we talk about the attacks that we have. We break them down into three categories. Implementation attacks against phones, configuration vulnerabilities, and then architecture. And now I'm going to hand it to Zane to cover the background information.
Thanks. Mic working? No. So we're talking today about SMS in the GSM world. And we're talking about testing SMS through the carriers. So no rogue base stations or anything like that. This is going through actual carriers. When we say SMS, we mean that as kind of a catch-all term for mobile messaging. So everything from like the basic text-only messages that we're all used to sending through multimedia messages, and then some other message types, things like EMS, which was a standard that never really took off, but it was supported by some Nokia and Sony Ericsson phones. So when we say attacking SMS, we mean really attacking mobile messaging in general. To us, the architecture is very simple. Because we're treating the carrier entirely as a black box, we have a very simple architecture like you see here. We have the sender on the left-hand side, and we have the recipient on the right-hand side. And when the sender wants to send a message, they send the message up to the carrier's SMS server, which is called an SMSC. The message gets stored there, and then it gets forwarded down to the recipient. So this whole system is called a store and forward system. And the reason for that is a lot of times the recipient is going to be offline. Their phone is going to be turned off. They're going to have no coverage, things like that. The SMS server can't just blindly forward the message down because the recipient may not get it. So the message needs to be stored on the carrier's SMS server until it can confirm that the recipient is actually online, and then the message gets forwarded down. It changes a little bit when it goes between carriers. Nothing noticeable to us as the user. If we're using this, it looks exactly the same going between a user, right? Or between carriers. If you're sending a text message to your friend that's on your carrier or your friend that's on a different carrier, it's completely the same. But it changes a little bit behind the scenes. So each carrier can kind of represent SMS messages internally using a number of different protocols. And carrier 1 and carrier 2 may actually represent it internally differently. So when they need to send a message between the two different carrier types, what happens is, what you're seeing with the cloud there, is it needs to be converted to some standard before it goes off to the other carrier. And what carriers typically do is convert the SMS to email, and then email it over to the second carrier. So you see here, let's say the sender sends it up, it goes up through one protocol in carrier 1, it gets converted to email, sent over to carrier 2, and then into another protocol and down to the recipient. Now, like I said, this has no impact to us as users. This has a huge impact to us as attackers, right? If you have to craft a very specially crafted SMS message that has specific bitmask header fields and a very, very specific layout to perform an exploit, if your exploit's now being converted through email and then to another protocol before it comes down to your victim, that's obviously going to have a pretty huge impact, and it's probably going to make your exploit not work. The other messaging type that we're going to talk about a lot today is MMS. Don't worry yet about all these different message types in here. The goal of this slide is to show that even though MMS looks to us, the user, as completely the same as SMS, there's actually a lot more going on behind the scenes here. You don't see that very straightforward, just the message gets stored in the SMSC and then forwarded down. Now there's a lot more messages that's going on behind the scenes, a lot of interaction between the sender and the carrier and the recipient and the carrier. So what makes this so interesting to attack? There's several reasons. Number one, mobile phone messaging, so SMS, is really an always-on attack surface. The way that SMS messages come down to your mobile phone is via one of the control channels, and this is the way that the network informs the phone that it has an incoming call and things like that. So this is really the core functionality of the phone, is the way that an SMS message is delivered. That means you can't really turn off that interface, because then your phone is no longer functioning as a phone. Your phone always needs to listen for SMS messages. In addition to that, that store and forward system I was just talking about is fantastic for us as attackers. Right? For those of us from kind of the IP networking and security background, think if you're trying to attack a remote system on a network, but that system is turned off. There's not really much you can do about that, right? It's not reachable, it's turned off. Here, the SMSC stores our attack for us, and when our victim comes back online, then it forwards the message down. So basically, it sits there and waits. It takes control of delivering your exploit for you, and it just waits until the victim comes online and then sends it down. It really means that SMS messaging you can always attack, really. Another reason is that there's much more functionality now over SMS. So SMS started out as a really basic service, right? We can write small text-only messages, things like that. There's not that much to attack. What do we have now? That's actually, you're going to be in our demo later. What we have now is a lot of functionality that's been built on top of SMS. Things like multimedia messages. You can send ringtones, videos, pictures, things like that. There's really much more to attack out there. And then finally, the hurdles involved in actually attacking this are really dropping. So let's say we found a bug 10 years ago in a mobile phone via SMS, and you wanted to exploit that. You needed to be an expert in likely a custom Motorola or Nokia operating system that the number of people who had the familiarity to actually write that exploit was very small. And what do we have now? We have smartphones and things like that that are moving towards commodity operating systems that a lot of people are already familiar with attacking. Right? Think about the number of people who have the necessary skill set to attack a custom Nokia operating system, and think about the number of people who have the skill set to attack Linux or Windows. Right? It's a much larger set of attackers now. And then finally, this functionality that I've been talking about that has been added on, things like MMS and things like that, it's been added on at basically built on top of SMS at higher layers. Now, for reasons we'll get into, at the most basic layer, there's not really much we can control as attackers. But all these layers that get built on top, we have full control. So as more functionality gets added, we have full control of that to start doing our testing. Those of us from the IP background side can kind of think of it like this. Let's say you're trying to attack a remote system, but you don't have raw socket access. So you can't really do anything at the IP layer or the TCP layer, but everything that's built on top of that you have full access over. So anything at like the HTTP layer, you could do any attack you want at that. It kind of maps back like that of the most basic SMS layer. We don't have that much access, but everything that's been built on top, we have full access to do whatever we want. What makes that all possible is something called the user data header. Now don't worry about all the specific hex in there. The point of this slide is to show what kind of a basic SMS looks like. Everything in blue is that basic SMS header, and when we're doing the style of attacking that we're doing here, we don't really have much control over anything in there. But everything on the end there in the payload section, so this is where when you write a text message, the text actually gets stuck down here in the payload section. We have full control over everything in there. And this is where something called the user data header gets inserted at the beginning when we're trying to use all that functionality that's been built on top of SMS. So all the things like MMS and ringtones and even multi-part concatenated messages use this user data header. So when you write a text message, just a simple text that's too big to fit inside a single SMS, what happens is the message gets split across multiple messages. And a user data header gets inserted at the beginning of each one. And it says, I'm a multi-part concatenated message. So when the recipient sees the message, it sees that it has a user data header, so it knows it's some additional functionality. And it reads the user data header and sees that it's a multi-part message. And each one will say, I'm a multi-part message, I'm part 1 of 2, I'm part 2 of 2. When the phone gets that, it stitches them together and it shows it to the user. Like I said, all of this that is now making all this functionality that's making use of like the user data header and being built on top of SMS, we have really full control over. Which brings us into, okay, how do we start setting up actually testing this stuff? To start testing, we need 3 basic things. We need a way to send messages, we need a way to actually encode those messages so they can be sent out, and then we need a way to receive messages. How many people had dial-up internet? Everyone at DSL? Anyone? Okay. Dial-up internet. Yeah? Okay. Do you remember the AT commands that we all had to play with our modems to get that stuff working? That's the sort of access you're trying to actually get to your phone again. So there's a GSM chip inside of your phone. And the way, from kind of a high level, the way that your phone communicates with that is via those AT commands. And so what we want to do as testers here is get access to that AT interface, because then we can issue our AT commands and send out messages onto the network. There's a lot of different ways to go about doing this. The simplest way, well, the way we started out with is that in a lot of phones, when you pair the phone via Bluetooth or connect it via a special serial cable to, let's say, your laptop, it will then expose the AT interface. So then you can just launch Hyperterminal or use something like PySerial or anything like that to connect to the phone and get access to that AT interface. And then you can start issuing AT commands to your phone. The ways you actually do that are sometimes via Bluetooth, sometimes via serial cable. It really depends on the phone. So the easiest way to do it is to get something like this. And this is just a GSM modem that plugs in via USB to your laptop. You plug it in, and you get access directly to the AT interface right there. So you can just slap that in and just start issuing commands to it. One of the interesting things, once we start getting more test equipment and rerunning a lot of these tests, is that the GSM chip is effectively a black box to you. You hand it an AT command, and it says yes or no. It either rejects it, and it doesn't send that message out on the network, or it accepts it, and it sends it out onto the network. But if it says no, there's not really much you're doing with it. Once we started testing different equipment, what we found is that some equipment would reject certain message types that we want to send out, and other equipment would actually allow it out. So when you're doing this testing, and if the test phone that you're using or the test GSM modem that you're using rejects a certain hostile message that you're trying to test, just try a different set of test equipment, and sometimes it'll actually let it out. So the next thing we needed, I keep talking about the AT commands. What you're doing is you're trying to send something called a PDU. It's a protocol data unit. It's really that slide a few slides ago with the blue hex and everything. That's really what you're handing to the AT command. It's a string of hex, and it's called a PDU. and the GSM chip then takes that and sends that out onto the network. So there's a few ways you can create those PDUs. We put a couple links in here for some tools that are really handy when you're getting started with this. Things like PDU Spy. It's a nice GUI tool that you can basically click a few options and it will generate that string of hex for you. And you just copy and paste it to the AT command and send it out. When you're doing a lot of this really low-level testing, though, quite honestly, you're going to do a lot of it by hand. Right? You're going to get familiar with this, and you're going to know which parts you need to change, and you really end up just kind of tweaking the PDUs by hand a lot. The last thing that we need is a way to receive messages. Now, this seems really straightforward at first, right? Everyone receives messages on their phone. The problem is we need much better access than that. Because by the time you see a message on your phone, two things have happened. Number one, the phone has decided that you should be allowed to see that message. And number two, the phone has probably altered something about that message. Now, when we're doing this testing, that's no good for us. We need to see exactly what came down off the network. We need that really low-level access to see what's going on. And the reason for that is, like in some cases, for example, like the concatenated multi-part messages, when your phone receives those, it doesn't show it to you, the user, until you've received all the parts of that message. So let's say it's a 3-part message. Until you get all 3, it doesn't actually show up on your phone. That's terrible for us as testers because we want to test different parts. We need to see everything that comes down. So the easiest way to do that, well, jumping ahead again, the way we started out with, which is not the easiest way to do it, is to find as old a phone as you can find, which we had a couple of these, old like Nokia 3310s laying around. And what we do is when the message, because these phones are so old, they really don't have much in terms of memory, and they really have no memory for SMS messages. What they do is when a message comes down to one of these, it writes it out to the SIM, and then it reads it back off the SIM to display it to the user. So we would have a message come down to one of these, we'd pop the battery, pop the SIM out, and you can get, we don't have it with us, but you can get a SIM card reader for about $30 on the internet. And we'd pop the SIM out, throw it in the SIM card reader, slap that in our laptop, and then use some software that we modified to read the raw PDU off of the SIM. And then we can see exactly what came down off of the network here. The easiest way to do this, though, is to just use one of those USB GSM modems again. Those are by far the easiest because you don't have to pop anything out. You don't have to do anything like that. You just issue another AT command, and it displays the PDU back to you. So really, the GSM modem is the way to go with testing. With that, I'm going to hand it back to Luis to talk about where we go next in our attack environment.
So now that Zane's talked about the testing environment, we're going to actually try to do some of these attacks and talk about what problems we ran into. So when you're testing, you have these are your goals. You want to increase speed, reduce cost, and be able to analyze issues. All these things are very difficult to do when you're using a carrier. And the reasons are, first, the speed. The carrier is really slow. If you're sending a test case, sometimes it can take, 10 seconds on a good day to get the SMS. And if it's congested, if the network's congested, there's sometimes backlog of an hour or a couple hours. Like when there's sporting events. When Michael Jackson died, all the networks went crazy. We talked to network operators that thought they were under attack until they turned on the TV and saw what was going on. So you don't want things like that to disrupt your testing. The other issue is cost. If you're trying to send 10,000 test cases, paying for each message gets expensive very fast. And you want to be able to analyze and debug. If you can move this away from the carrier, let's say to Wi-Fi or something else, then you can run Wireshark, look if you are actually sending what you think you're sending, or if you've constructed something wrong. And to the people with open BTSs in the crowd, we did not have access to that when we were doing our testing, so these are the methods we used. First, we used a system that was originally used by Colin Muelliner. He might be here in the crowd. I know he's in the conference. So basically, you create a fake MMSC, and you use Canel and Apache. You need to add a new MIME type to Apache to be able to process MMS. And this is currently fully working for Windows mobile phones. Windows Mobile 5 works right out of the box once you add your MMS server. And for Windows Mobile 6, they made some changes. So we found an undocumented registry key that you need to modify to be able to use this system. The key at the bottom lists what ports only listen over SMS. So if you want to do a WAP or whatever, you just remove your entry from this registry key. So looking at MMS gives us a lot more vectors. We have all these different types of packets, and these different types of packets all have headers, which provide an avenue for attack. And on top of that, we have the actual MMS contents. First is Smile. Smile is a form kind of like HTML, but very cut down. Then you have the content. You have images, you have audio codecs, you have video codecs. So these are some of the challenges that we came across against testing Windows mobile phones. The latest version of IDA Pro comes with a new debugger for Windows Mobile, version 5.5. This fixed a lot of issues that were in the debugger previously. It fixed a lot of bugs, but when it comes down to it, for almost everything, you're reliant upon ActiveSync. ActiveSync is the way that you're able to debug and set up a syncing relationship between your computer and the phone. I don't know how many people have had or have Windows mobile phones, but the first time you connect it to ActiveSync, it's going to prompt you and ask you, do you want the internet connection to be routed through your PC? Yes or no? No matter what you select, when you receive an MMS, it always tries to route through your PC. What that means is if you're trying to test an exploit live over a carrier network, you cannot do it with an ActiveSync debugger. You have to either test it with a virtual setup or find another method. I've been told that BinNavi, its debugger, it can work over Wi-Fi, but we don't have BinNavi. We're not able to test that. In either case, there's general issues with Windows Mobile. You can't step into system binaries. They're a different type of format, so no matter what debugger you have, you can't step into the system binaries. And by default, you can't even copy the files off. There's a couple of tools here that will pull the files off and reconstruct them so you can do static analysis in IDA, but you're not going to be able to do runtime analysis. We also looked at the iPhone 2.x firmware. So this doesn't even have MMS, so it cuts down our attack vectors. The debugger that's available is GDB. Apple maintains their own tree for GDB and GCC. The reason they do this is that OS X and, in turn, the iPhone support the Mach kernel. So they have all these customizations to be able to use the Mach kernel. One of the problems is that they usually rely on very old releases. The current one, I think, is based on 2005, and they just do patches to be able to work with their system and a couple of bug fixes. So all the newer features available in GDB aren't available for the iPhone. GDB server is broken. We weren't able to use that. The newer versions of IDA have a GDB server plugin, so you'd be able to debug remotely using IDA, but the GDB server is broken. A lot of these phones are going to have watchdog processes. If the phone process dies, they want to be able to restart it so the user experience isn't modified. Like if your phone process crashes, it'll restart. Maybe the user won't notice. So when you're trying to debug, you can't sit at a breakpoint too long because there'll be various timers that will be set, and then it will kill your process and restart a new one. So the iPhone 3.0 finally supported MMS. It's for images only. It does not support audio. It does not support video. So that also cuts down some of your attack vectors. The same GDB issues apply from 2.x to 3.x. Sometimes you need to apply entitlements. Entitlements are just kind of like permissions for a process. So you apply entitlements, and that allows you to debug that process. And then we're going to move on to attacks. The first category of attacks we're going to cover are implementation attacks. These are attacks against the messaging software on the actual phone. Issues that you'd find here would be like buffer overflows, integer overflows, memory corruption, your standard software security type issues. The first thing that we found is an issue that was in the Android platform. and this resulted in a denial of service. The issue relates to concatenated multi-part messages, as Zane was talking about. So if you have a 3-part message, it'll be part 1 of 3, part 2 of 3, part 3 of 3, and each of these has a sequence number, the 1, 2, 3. And according to the spec, the valid range is from 1 to FF. So of course, we sent a multi-part message with a part number of 0, and it resulted in a crash. One of the very interesting things for us is that we assumed that a crash would happen in the messaging application. But what ended up happening is the crash was at a much lower level. The crash actually resulted in the phone process crashing. That meant not only could we not send or receive text messages, we could also not make or receive phone calls. Android, like other phones, also has a watchdog process which will restart the phone process if it crashes. So this is a temporary denial of service. This is another denial of service, but this one's really cool. This was against Swirly MMS, which was the third-party MMS client for the iPhone, and this resulted in a perpetual denial of service. Similar to the previous case, upon an attacker sending a malformed message, the phone process crashes and you can't make or receive phone calls and you can't send or receive text messages. However, this issue lasted across reboots. If you try to reboot your phone, it comes back up and the phone process is still crashed. The reason this works this way is to describe a little bit about how a message gets delivered by a carrier. When a carrier sends you an SMS message, the carrier sends the message to the phone, and the phone needs to send an acknowledgement. Because maybe you're on their network, you walked into a store that has very little coverage. So they sent the message, but you didn't receive it, so the carrier will keep trying to send it to you again. What happens in this case is that the crash is so early in the processing of the message that the acknowledgement is never sent. The carrier then thinks that you never got the message and will keep sending the attack for you. The only way to clear this attack from the phone, we discovered, was to physically remove the SIM card from the phone, place it into another phone. That phone has to register onto the network and clear the message. This next category of attacks are very interesting to us. This was an attack that affected Windows mobile devices, but was not necessarily in Windows Mobile. This is pretty much the holy grail of SMS attacks. An attacker sends specially crafted message to these affected Windows mobile phones. This message contains the location of a binary on the internet. The phone, upon receiving the message, downloads the binary and executes it in the background silently without notifying the user. There's no depth to worry about, there's no offsets, you don't have to worry about anything. You can write your binary even in Visual Studio, there's no shellcode, it just executes. This vulnerability was posted publicly to the forum that's listed there, and what's most interesting about the attack is how it came about. And to describe that, we need to talk about how a phone reaches the public. Usually there's 3 groups involved in delivering a phone to the public. There's the operating system vendor, in this case Windows, and then there is the OEM. The OEM manufactures the phone, writes drivers and customizations for their hardware. And the third group is the carrier. The carrier will put modifications, customizations for the phone to make it work as best as possible on their network. So there's these 3 different groups. And if one of these groups changes something, it could have unexpected consequences. What happened here is that legitimate administrative functionality that was present on the phone in Windows Mobile was left open to unauthorized users. So this is legitimate functionality. Within the MSDN, it describes what permissions it should have, and before shipping the phone, the OEM changed the permissions so that it would process these messages received from anyone without any authentication. So this is quite different than what we're used to in standard software security. What we're used to is one vendor provides a product, they're responsible for the security of that product. Here we have 3 separate groups that all affect the security of the product, and if one of them makes changes without notifying others within the group, it results in security issues like this. And we think that we're going to see a lot more of these issues as we move along, because people are trying to release products fast, and they're just trying to ship them and make them work on their network as soon as possible. And with this, Zane's going to cover architecture attacks.
So one of the first questions that we had when we started this research was, okay, how much is there really going to be to attack, right? Because when we first started going into SMS, we had no background in SMS. We just kind of thought of it as, you know, way you can send text messages and maybe a few pictures or things like that. Once we started diving into it and reading the specs and all the technical docs around SMS, what we found is that there's really a whole lot of functionality that is performed via SMS. A whole lot of other types of messages that we're not used to seeing. The carriers really use SMS to perform a lot of different administrative functionality to the devices on their network. And when you think about it from their perspective, that makes sense, right? Because put yourself in the carrier's shoes, you have a lot of different devices on your network, and you need basically the lowest common denominator way to deal with all these devices. SMS really fits the bill for that really nicely, because even the most basic phone really supports SMS. So the carriers can use SMS to perform different administrative functionality on the phone. And the way they do that is by sending messages that are certain specially crafted SMSs. And when your phone receives one of these message types, it doesn't just display the message to you. What it does is it looks at that message and says, oh, I know what this is. This is an administrative message. I'm supposed to do some sort of functionality based on that message. The most straightforward example of that is voicemail notifications. So one of the ways that the carrier can notify your phone that you have a voicemail waiting is by sending you a voicemail notification SMS. And when your phone gets that SMS, it doesn't display the message, the content of the message to you. What it does is it performs an administrative function on the phone, like popping up a new screen that says you have a voicemail waiting, or popping up an icon in the corner saying you have a voicemail waiting. So what did we do as security people? We see something like that, we instantly wonder, what are the protections around something like this? So we read through the spec, we figured out how to write one of these messages, and we wrote one out, and we sent one to our test phone. And this is what we got. It's kind of hard to see because of the lighting. But we triggered 42 new voicemails waiting on our test phone. This message obviously never came from the carrier. This came from us. But the phone still behaved and performed that administrative functionality just as if this came from the legitimate carrier source. Right? Voicemail notifications, that's no security impact. It's really just a bar trick, not an actual security test. But what we did is we took the lesson learned from that we were able to generate and send a message type that should clearly only ever come from the carrier, and we kept reading through the specs. And one of the things we came across are things called OTA settings. So OTA settings are a way that the carrier can push down new settings to feature phones. So feature phones are the ones that we had before smartphones. And this is a way a carrier can push down, maybe something changed in the carrier network, they need to push down new settings to the phone. This is one of the ways they can do it. So we took the same approach again. We wrote out an OTA settings message, we sent it down to our test phone, and this is what we get. New settings received, installed, yes or no. Now this screen is scary for 3 reasons. Number one, just like the voicemail notifications, it worked, right? This came from us. This didn't come from a legitimate carrier source. This shouldn't work. Number two is, and this is really a much larger problem in mobile security, the complete lack of context here, right? The user is being asked to make some sort of decision that is very security sensitive, right? New settings have been received, install yes or no. What settings were received? Where did these settings come from? What is any sort of contextual information that you would need to actually make this decision correctly, right? I'd say most of the people in this room are serious security experts. How could any of us possibly have the right information needed to make this decision? Which brings me to number 3, the third reason why this is scary. The setting that we're changing with this message is the internet proxy value for this phone. This means all of this phone's internet traffic now comes through our proxy, where we sniff and man in the middle all of this phone's internet traffic. So remember at the beginning when that MMS architecture slide mentioned all those messages going on in the background? We took these same lessons, we went back and we looked at that again. So what you're seeing here is a very kind of high-level, basic overview of how conceptually MMS works. The sender pushes content up to the carrier's MMS server. This is the point where once that content's up, so the content is like the picture that you took or the video or things like that. Once that content is up there, the carrier applies a number of protections there. They scan the content for malware, for viruses, for known exploits, for spam, things like that. They apply their anti-spoofing protections. They do all their protections at this point. Once that they feel safe with that content, they generate one of these specially crafted messages, the notification message, and they send it down to the recipient's phone. When the recipient's phone gets that, it goes, OK, I know what this is. This means I'm supposed to go fetch my MMS content from the carrier servers. What did we do? Took the same approach. We wrote our own notification message. We send our own notification to the victim. And now, our notification points to our attack server, not the carrier's MMS servers. So this means we host all of our content on our attack server, which means our content never went through any of those carrier protections. So I keep talking about the content. What's actually in that content? It's really just a binary file, usually ends in .mms on a carrier server somewhere. And it's made up of 3 parts. It's made up of headers, some SMIL markup that Luis talked about, basically HTML, and then the actual message content, so things like the picture, the video. What's in the headers? Well, there's things like transaction ID, version number, things like that, but there are 2 very important fields to us. They're the date and the from. This content was on our server. This content never went through the carrier. We have full control over the date and the from fields. That means we can arbitrarily backdate this message to any date we choose, and this means we can spoof the source number for any number that we choose. So we've completely bypassed the source spoofing protections, as well as all of the antivirus, malware, known exploit checking that's going on in the carrier. And in addition to that, we get a bonus vulnerability. We're able to use this to remotely fingerprint mobile devices. So when the victim's phone comes to our attack server to get that content, the way they fetch that content is via an HTTP GET. And what goes along with GETs? User agents. So we watch on our attack server for the user agent that comes in for a specific attack that we sent out. And these are some example user agents from some of our test phones. We're able to use this to fingerprint a remote mobile device, and then we launch one of the very specific implementation flaws or configuration flaws to take control of that mobile device. So I want to hand it back to Luis to talk about the proof of concept tool that we wrote for this.
So presenting Taft. There's an attack for that. This is an app that we wrote for jailbroken iPhones. It supports a lot of the attacks that we've been discussing here. And the MMS functionality is actually, we wrote a web app that goes with it. And I'm going to describe that really quick. The sender running Taft is going to push content. So the content is what you saw on the demo screen. The source phone number, any date modifications, and the text payload. The web app gives us back the MMS file name, which we're going to use for the notification. And then the receiver, the target phone, pulls down the content as if it came from the carrier. So we have some more demo. So this is this first part is the same demo we saw before, where we see that it's contacting the server, it's contacting the web app, it's going to send the notification. And now we understand a little bit more about what's actually going on. And on the right-hand side, we're going to receive the spoofed message. There we see that it came from 611. This is the same thing as before, but now we understand what is actually going on. So we were able to completely spoof source numbers, and we decided to see what else we could do. Something that you'll notice if you see the to field, we hardwired our phone numbers because we don't want anyone here getting our phone numbers. But so we have successful spoofing against with the arbitrary source number. So we decided, what if we can put text? Maybe we don't know what contacts they have, so we can just put arbitrary text. So we just pick the name out of random. So for example, we just pick Steve Jobs. And then we're going to send this message across the network. And we ended up doing all this development on a jailbroken iPhone because we needed certain features that weren't available for the standard SDK. And I think we felt a little bit guilty that we weren't doing what Steve wanted. Steve wants us to use the real SDK and put it in the App Store. And we've always wanted Steve to tell us it's okay. So hopefully when this message comes across, we will have his permission. So there we have a message from Steve Jobs. We can spoof arbitrary text in the front field, and it's telling us to upgrade our iPhone and get it jailbroken. So it's okay now. So this is an architectural issue at the carrier. What this means is it is not a quick patch. It takes a while to get fixed. We disclosed to the carrier that we were testing with and told them about the vulnerability. And what they told us, it's going to take them a while to fix. They can monitor for this type of activity, and we've been told that they are, at least in the network we tested against. And we think that various carriers are affected. Obviously, we can't test in all the carriers around the world. So what we did is we contacted the GSM Alliance, which is an umbrella organization that lots of carriers belong to, or I think all the carriers belong to. And they've been distributing the information to individual carriers.
So what did we learn from our testing? We learned that there are a whole number of different messages that are only ever supposed to be generated and sent from the carrier systems. And we learned that in our testing, a lot of the different messages, actually, we are able to generate and send as attackers. We learned that this whole different interaction between the OEM, the vendor, and the carrier can cause very serious security vulnerabilities when they start playing with the device and not telling anyone. And then we learned that in a lot of cases, users of mobile phones are being asked to make very sensitive security decisions with, in some cases, practically no context. Right? Users are going to need a lot more contextual information than we saw in that example to be able to make the correct decision there.
So the bottom line is that attacking SMS in the past was very difficult. Attacking SMS now is much less difficult, and attacking SMS in the future is going to be even easier. Thank you for coming to our talk.
Thank you. We've got some minute for questions. Any questions?
So the conclusion would be that the carriers have to filter the user data header before they send messages. Is this correct? So the solution would be that the carriers sanitize the user data header before they send the SMS to its customers.
Yeah. What we thought is that when we reported the message, that someone at a console would be able to change a filter and it would be fixed within maybe a few days if they were going to do testing. And what we've been told is that any change to a network usually requires 6 months to 1 year testing before it's allowed on a production network.
So yeah, in theory, yes, sanitizing the user data header is the right way, right? Like the notification message that we were sending and those carrier messages that we're sending should never come from us as a mobile endpoint there. That should only come from the carrier system. So yes, in theory, in practice, there's a whole lot more going on there.
That also means that they are monitoring is probably also a software change, isn't it? So.
The monitoring systems may be different than the actual systems that route messages, but we don't work for carriers. We don't know. It's pretty much a black box to us.
It looks like this. So, yeah. Any more questions?
Well, the first is actually a comment. There's not only 3 parties involved in the phone development. There's way more parties involved in that. And I mean, this may also be the operating system kernel vendor of the baseband. You have the actual the baseband chip vendor and so on. And those vendors, they talk very little with each other. So the problem is actually aggravated quite significantly from only those 3 entities. So I would expect way more problems than you would probably expect in that area. The second thing is that all of that, as soon as you incorporate a network, of course, all of that doesn't help anymore, right? So you say, well, the carriers need to add the filtering and so on, and need to put all this in their network. But all that only is the case if you're actually using an official network. But if anyone just sets up a fake network, then all of these network-based protection mechanisms are circumvented, and since there's no authentication involved, anyone can just do that. So while it is, yes, it is a fix for the core network, but it doesn't address the fundamental problem that there is a lack of authentication.
Yeah, absolutely. I mean, like we said, our testing was focused on going through the network, and yeah, that's a whole other area definitely of if you're going to a fake base station.
One more question? Okay, thank you. Was very interesting.
Thank you.